All right, we are in geometry. Today's date is Monday, March 11th. Please put it on your papers. March 11th. Make sure your name is on your papers. I've been telling you guys to put names on the papers because when I go through your binder, it's really nice to just randomly open to a page and be like, oh, this is Beverly's binder because it says Beverly's name on notes 8-6. I just randomly picked that page.
And you also know it's my binder because it says my name. It says
That also is very, very helpful. All right, so on Friday, we learned about the Inscribed Angle theorem. It's the easiest theorem in all of geometry, maybe, I think. There's probably a theorem that says all circles are similar. That's also pretty nice. What is the Inscribed Angle theorem? Use this picture off to the right. We have this red dashed angle and this blue solid angle. What do we know about the relationship between those two angles? And for those of you that didn't watch the video, that's okay. You're learning it now. How can we summarize that 10-minute lesson into one sentence?
Don't you either just multiply or divide by 2?
Yeah, Martine. Multiply or divide by 2. So let's all write this down. Let's assume that we have this angle here. Let's call it theta. This angle, I'm going to call it theta. Now I have to use Martine's rule. Martine says either multiply or divide by 2 to get to the other angle. Well, Martine, it's still up to you. I have a big angle here and I have a smaller angle there, so therefore this angle must be... All right, so you told us multiply or divide by 2. So is this going to be 2 theta or theta divided by 2? It is indeed theta divided by 2. Thank you, Martine. You can turn in your card. All right, I have to come over here to Classcraft. Martine... There you are. Let me get the marbles going here, too, in a sec. All right, but this is what I want us to write down for the Inscribed Angle theorem. So the Inscribed Angle. I cannot spell inscribed. Inscribed. Thank you. I appreciate the confidence. Inscribed Angle is 1/2 of the central angle. That's it. Sounds like we're having side conversations in the back desk. If that continues. Your side conversation is not about math. The circumference of pi. That is a very, very deep question because it doesn't even exist. I mean, the circumference uses pi. All right, so from there, other implications. So Friday we learned about one implication, which was, and I'm going to briefly sketch this here just so I can remind us, you do not need to write this in your notes. One implication is if I have another inscribed angle, say I have an inscribed angle over here, this yellow inscribed angle right here is the same angle as the red angle. These two inscribed angles are the same as long as they intersect at BC. We will be using that today. Make sure you remember that. This yellow angle and this red angle are congruent. If you need to rewrite that in your notes because you forgot it on Friday, you can add that to your notes. But let's continue on. One other implication is that if BC, Jaden, if BC is the diameter, then what do we know about this blue angle? Quiet raised hand. What is the measure of this blue angle if BC is the diameter? What does it measure? How many people know this? Only India. That's not good. I'm hoping for more hands. I'm going to wait. What is the measure of that blue angle? What is the measure of a line? Ah, there's more. Emily, go for it. It is indeed 180 degrees. Then this measure of angle BAC is, as Emily told us, 180 degrees. I need to practice writing my 8s the other way. There we go, 180 degrees. And then what do we know about this red angle, BDC? So let me give Emily her marble and Emily her XP. What do we know about this red angle? This red angle, the measure of angle BDC. BDC. What is that to measure? Anna. Which is? It is indeed 90 degrees. This is a kind of little fun fact because it relates to our last unit. Our last unit dealt with triangles. The majority of the time, we're going to get rid of those hard theorems, law of cosines, law of sines, not using those hard theorems because those applied to triangles that didn't have 90-degree angles. This is a triangle that does have a 90-degree angle. Go ahead and write that little symbol. Whenever you have the diameter as the hypotenuse of this inscribed triangle, see this triangle? This is the hypotenuse, BAC. This line, BAC, is the inscribed, all right, I guess it's the diameter, which is the hypotenuse of this triangle. This triangle is inscribed because all three of the vertices, all three of these points lie on the circumference. Whenever that's the case, you will always, always, always have a right triangle, which means you can use all of our right triangle theorems that we should have known by now. We know how to use Pythagorean Theorem. We know how to use all of these sines, cosines, and tangents. All of those theorems are suddenly unlocked because we have a right triangle. Thank you. All right, so let me give Anna her XP and her marble as well, and then we can move on. Are there any questions up to this point? That's kind of a big, fun theorem. It allows a lot of math to happen.
How close do we to a pizza party?
We are that close to a pizza party. It needs to hit the very top where I can barely get the lid on the top.
Bro.
We already hit our no homework.
We don't even have enough marbles to do that.
We do. We have exactly enough marbles, actually. Unless someone stole them. Hopefully that didn't happen, because then you don't get a pizza party. All right, so
Definitely want us to do marbles.
let's look at an example using one of these other implications. So now we know BC is the diameter. I'm telling you that. I need to find the radius of the circle. I need to find either this length BA or this length AC. How am I going to do that? All right, quiet raised hand. I see India's ready to go. How am I going to do that? India has an idea. You can still raise your hand if you don't have your card. Just means I'm not going to give you preference. I can still call on you though. Only 2 people know. Let's hear from India.
I would do is I'd do Pythagorean Theorem doing a square plus b squared equals c squared, and then whatever c squared is, I divide that by 2 to get half of that length of the hypotenuse.
Well said, yeah. All right, so everyone write it down. This is Pythagorean Theorem. When I add the 2 legs squared, so this is my red dashed leg, my other red dashed leg. When I square those 2 and add them together, India told us that should be the hypotenuse squared. That is Pythagorean Theorem. And India says we can solve for this hypotenuse. But once we solve for that hypotenuse, we just have to divide it in half, because half of the diameter is the radius. All right, I need another person to use India's strategy to fill in Pythagorean's theorem. So thank you, India. Someone use India's setup. I have 2 people, 3 people. Ellery, go for it.
3 squared plus 4 squared equals c squared, which is 9 plus 16, which is 25 equals c squared. You take the square root, so you have 5 equals c. So 5 is the diameter, and then you divide that by 2 to get the radius. So your radius is 2.5.
Dang, so fast. And everything you said is correct and well enunciated. I'm going to go back and review everything that you just said. Thank you so much. I'm going to put your marble in, give you the XP right now. Oh, going too far down. Ellery, boom, 50 XP. All right, so Ellery has told us how to fill this in. We're using this length, 3, this length, 4, and plugging in 3 and 4. We plugged in 3 and 4 for our legs. Ellery also squared 3 and squared 4. Square of 3 is 9, square of 4 is 16. Have I lost anyone this far? No one is lost. From there, Ellery also combined 9 and 16. She said when you add those, you do get 25. And you still have a c squared on the right-hand side. And then Ellery told us that we needed to undo this square. To undo that square, she took the square root of both sides. The square root of the right side, the square root of the left side, and Ellery told us that that whole diameter, that hypotenuse of the inscribed triangle, is a square root of 25. Square root of 25. Got some accent there. And that is 5. 5. So that represents this entire hypotenuse. That entire hypotenuse is 5. But that's not what we're looking for. We're looking for half of that length. We're looking for the radius of the circle. So half of 5, and the answer is indeed 2.5. Thank you, Ellery. Thank you, India. 2.5. 2.5. Inbox it. All right. We are on to example 2. I'll leave that up on the board, though. We are on to example 2. Ask me questions about example 1. You will be seeing a few of these questions on tonight's homework. Tonight's homework, we have 2 different problems. Example 1 and example 2 are from problem set 1, and example 3 and 4 are from the second homework assignment. No questions? I'm moving on to example 2. Example 2. All right, so we have EC, arc EC. So if I wanted to be formal about this, I could put this arc symbol above EC and this arc symbol above BD. Fun fact that you guys probably don't care about, in Microsoft Word and basically every programming language, aside from some custom things in LaTeX, you cannot make this symbol. So I just put arc out front. But arc EC, I'm talking about this arc right here, this EC. This arc EC right here is 60 degrees. Everyone label it, 60 degrees. And that other arc, BD, so this arc over here, measures 80 degrees. Label that one 80 degrees. I need to keep writing my 8s like this. 80 degrees. Somehow, we need to use those 2 facts and this diagram to find the measure of CFB, CFB right here. This is our question mark. How the heck are we going to do that? Ooh, that's hard. And I think this is such a hard question that I'm going to pause this and let you guys think about it. There are a few different ways to approach it, but I think, as far as I can see, there's only one way to solve it, but that doesn't mean there's more. All right, so we're back. This one was hard, but I will give you all a hint now. I can tell you exactly what this angle is. This yellow angle right here, I can tell you what that is. A lot of people were trying to find this angle and saying it was 80. That isn't quite correct because F is not the center. The center is A. So because it's not a central angle, we can't actually figure out this angle right away. I mean, we could eventually find it, but I can immediately tell you what angle DEB is. Is there a quiet raised hand out there that can tell us what this measure of angle DEB is, this yellow angle? And it's by using this theorem at the very top called the Inscribed Angle theorem. Is there a quiet raised hand out there that wants to take a guess as to what this yellow angle is? I see one hand. Yeah, go for it, Anna. It is indeed 40. Why?
It's half of 80.
It is half of 80. All right, everyone write it down, and then we'll try to understand it after you write it down. All right. This is an inscribed angle. The normal central angle would have been the angle that went between BA and DA. That would have been the central angle. But this central angle is double this inscribed angle, or this inscribed angle is half of this 80 degrees. Half of 80 is 40, which means I can find another angle on here. I can find this green angle down here. Is there a quiet raised hand that wants to tell me what this green angle is? And I'm looking to call on people that still have cards over people that don't have cards, if possible. Yeah, Beverly. It is indeed 30 degrees. Thank you, Beverly. All right. There's Anna's marble. There's Beverly's marble. All right, make sure you have those 2 written down. Anna and Beverly.
With the what?
All right, gentlemen, please stop distracting us. Jaden, you're losing marbles.
Why did you take a whole handful?
I took 1 marble.
One with 3 fingers?
So from there, I should be able to figure out what this black angle... All right, you guys are losing more marbles. I should be able to figure out what this black angle is right here, because there are 180 degrees in a triangle. Can someone tell me what that black angle should be? Colby.
110.
110. How'd you get 110?
You just 180 minus 70.
180 minus 70. So you took 180 degrees in a triangle, and then you subtracted this 40 degrees plus this 30 degrees.
I don't realize it was good.
40 plus 30 is 70. 180 minus 70 is indeed 110. And then Colby, therefore, this measure that we're trying to find is 110. Ooh, that's too many ones. 110 degrees. All right, Colby, you got a marble. Thank you. And you got some XP. I need one final volunteer to tell me why. That last part where Colby was able to get from this side to this side, what theorem did Colby just use? How many people know this name? Ellery. It is indeed by vertical angles. Thank you, Ellery. All right. We are moving on to example 3 and then finally example 4. Let's get through this a little bit quicker than we've been going. Example 3 is a little bit hard, so I do need to spend some time on it, but example 4, we can do it in about 30 seconds. Example 4 goes really fast. All right, we have this quadrilateral, D-E-A-R, deer, is inscribed in circle P. I need to find this measure of ARD. This measure down here, I'm going to do it in yellow again. ARD, what is this angle down here in the bottom? What is the measure of that angle R? How am I going to find that? And I want to give you guys time to think, so I'm going to give you guys 30 seconds, and then we'll come back. All right, so we're back, and here is the trick. The trick is only look at this angle right here, this AED. If I'm looking at these red lines, then I can tell you what all of this arc adds up to. I should do all that arc in a black line. All of this black line arc, this arc right here, I can tell you exactly what the measure of that black arc is. By the inscribed angle theorem, it must be double this inscribed angle. That means that this measure of the arc is twice of 120. Therefore, this black measure is 240 degrees. That is a great question. How does that help us? I'll ask it back to you guys. Well, how does that help you find this green measure, this arc of the green measure over here? How can we use the fact that 240 degrees is on one side, that green measure is on the other? What is the measure of that green arc? How do we find it? Anyone have an idea? Yeah, Ellery? Exactly. These two arcs, the green arc and the black arc, must add to 360 degrees. That's just a full circle. A full circle is 360 degrees. So 240 plus what? This green adds to 360, so I just have to do 360 minus 240 to get to the green measure. So the green measure must be 120 degrees. We're copying this down. That green measure must be 120 degrees. I don't see some pencils moving. And then from there, use inscribed angles again. Inscribed angles say that this yellow angle that we were originally trying to find must be half of 120 degrees. Aurelio, please step outside. You can just sit down outside. Leave the door open. Half of 120 is 60. This yellow angle is 60 degrees. Question?
So the angle AED is also 120. Is that just a coincidence?
It is just a coincidence, yes. Maybe I should have chose different numbers so there would be no confusion.
This, you can only do the inscribed angles when you have like the angle of the arc length. It's not the actual angle inside of the shape inside the circle.
So if you have either one of them, you can find the arc length. For example, if I have 100 degrees here, I know that this whole length right here is 200 degrees.
Right. But, okay.
So,
All right, and that brings us to our inscribed quadrilateral theorem. Another easy theorem once you know how to apply it. It's easy to remember. Opposite angles. Well, what do you notice about these opposite angles? 120 and 60. These are opposite of one another. They're across the shape. They're on the other side of the shape. Therefore, they're opposite. What do these two add up to? Go for it, India. 180. Yep. And India, do you remember the term that we've been using for whenever things add up to 180? It is indeed supplementary. All right, so here it is. Opposite angles in an inscribed quadrilateral are supplementary. And I know that's not going to help some of us, so we will say add to 180. I need to start writing my 8s this way. 180 degrees. Just look all the way across and make sure that they add to 180. That's all there is to it for quadrilaterals. Let's see if someone can apply this theorem to example 4. I'm scrolling down now to example 4, leaving that up there. I want to find the measure of angle PAR. PAR is this angle right here. What is this angle? PAR. Quiet raised hand. Anna knows. Who else knows? India's ready. Jaden is ready. Yeah, Jaden, go for it.
I wasn't raising my hand.
You're just stretching over there because you're about to fall asleep.
Okay, so I think the angle is. I don't. Let me tap somebody in. Oscar. I choose you.
Alright. I think the angle's I don't know.
Oscar, can you identify the angle that is opposite of this yellow angle?
40 oh. Is it P and K?
Is it P or is it K? It's one of those two.
Okay, it's obviously K.
It's K. And what do we know about those opposite angles?
They're supplementary.
All right. Therefore, they both add to.
190.
So this unknown angle x plus that 43 is equal to 180. Thank you, Oscar. These two angles have to add to 180 degrees. From there, I simply subtract 43 on both sides. Who wants to do a simple subtraction problem to get their participation card in? Oscar just got his marble and his points.
I didn't get any.
Sadly, no.
Oh, last time I stretched on the
Yay, that's a good thing, actually. All right. Go for it, Ellery.
Oh, well, I just had a question, but
Oh.
it's 137.
What was your question?
Could you have done this on the problem, the previous one we did in example 3?
Exactly, yep. I could have just skipped and been like, what is 180 minus 120? 60, done. Yep. I was just showing you the long way, the kind of proofy way of doing it. There it is, 137 degrees, box it, final answer. Ellery got her marble, Ellery got her XP. Are there any questions about today's lesson? All right, go ahead and write your summaries.